Hello dear students, this is grade 12 mathematics lesson on unit 2, which is introduction to limits and continuity. So for today's lesson we focus on limits of a sequence. So after completing this lesson you are expected to determine least upper bound and greatest lower bound of a given sequence. In addition to that, you are expected to evaluate limits of some sequence, and you are expected to identify monotonic sequence, null sequences, and you are also expected to identify convergent and divergent sequences. So now let's proceed to the lesson. Let's see about upper bounds and lower bounds. Let's see the definition. We have this sequence A and B sequence, and these two small m and capital MB element of real number. Then this capital M is said to be an upper bound of the sequence if this M is greater or equal to with all elements of the sequence, or AI, where AI is element of the sequence. And this small m is said to be it is a lower bound of the sequence AN if the small m is less than or equal to AI, where AI is element of the sequence. That means this M is less than or equal to all elements of the sequence. Now we say a sequence is bounded if it has both an upper bound and a lower bound. So we say a given sequence is bounded if it has an upper bound, both an upper bound and a lower bound. And from the upper bound, the least number, we call it is least upper bound or lab of that sequence. That means the smallest number from the set of upper bounds of that sequence is called the least upper bound. And the greatest number from the set of lower bounds, the greatest number, we call it is greatest lower bound of that sequence. Now let's see example for this concept. Now let's try to find the upper bound, lower bound, the least upper bound, and the greatest lower bound of this sequence. To find this, we need to list some terms of this sequence. The first term of this sequence, if you put 1 here, you get -1. When you put 2, you get 1/2, -1/3, 1/4, and it goes on like this. So when you see this sequence, if it goes on like this, at infinite term, this will goes to 0. So it starts from -1, 1 over 2, negative 1 over 3, 1 over 4. As you can see, the denominator is getting bigger and bigger. So at infinity, the term will proceed, or it goes to 0. So when you see the elements of this sequence, or this sequence is found between negative 1 over 2, the smallest number from this set is this negative 1. Negative 1, 1 over 2, negative 1, it's going like this and goes to 0. So the smallest number from this set is negative 1, and the biggest number is 1 over 2. Next 1 over 2, it goes on, it decreases. So the greatest number is 1 over 2 here. So this sequence is found between these two numbers. It's found between negative 1 and 1 over 2. So we have negative 1 here, and 1 over 2. So this sequence is found between these two intervals, open interval. So any number greater than or equal to 1 over 2, this part, it is an upper bound of the given sequence. And any number less than or equal to negative 1, this part, this it is the lower bound of this sequence. So its upper bounds of the upper bounds of this sequence are numbers which are greater than or equal to 1 over 2. The upper bounds are numbers which are greater than or equal to 1 over 2. And its lower bounds are all real numbers which are found less than or equal to negative 1. So from this set, it is least upper bound. From the upper bound, from all numbers greater or equal to 1 over 2 are upper bound. From this upper bound, the smallest number is this 1 over 2. Therefore, 1 over 2 is this the least upper bound, and negative 1 from the lower bound. Lower bounds, it's negative. The lower bounds are numbers which are found below negative 1, including 1. Therefore, from this set, the greatest lower bound is it is negative 1. Therefore, the GLUB of this sequence is it is negative 1. Now let's proceed to another example. Let's see this one. This sequence is given. We need to find its least upper bound and greatest lower bound. So to find that, we need to list some of the terms of this sequence. So when you just list the terms of this sequence, the first term, when you put 1 here, to the power of 1 over 1 factorial, it is 2. The second term, put 2 here, 2 squared over 2 factorial. Therefore, this is 4 over 2 squared, it is 4. 2 factorial is 2. 4 over 2 is this 2. So it goes on like this. The next term is 4 over 3, 16 over 24, 32 over 120. It goes on like this. When you see the terms, look, the denominator is growing faster than the numerator. Look, this one, this number is bigger than the numerator. So this term, if you just proceed at infinity, this term, it goes to 0. It goes to 0. Therefore, the set of, or the elements of this sequence found between 0 and 2. As you can see, the minimum, this sequence is decreasing to 0. So the smallest number is 0, and the biggest number on this set is 2. So our sequence this is found between 0 and 2, including 2. Therefore, from this set, its upper bounds are all numbers which are found above 2, including 2. Look, you can see this one, this set is found between 0 and 2. It includes 2. It doesn't include 0. So all numbers above this, including this border 2, are the upper bounds, and all numbers which are found below 0, including 0, these are the lower bounds. Therefore, its lower bounds are all numbers which are less than 0. Least upper bound, its least upper bound from the upper bound, the least number is this 2, and the greatest lower bound from the lower bound, the greatest number is this 0. So this is the answer. Now let's continue to the third example. Let's see this one. This sequence is given. We are asked to find it is least upper bound and greatest lower bound. To find that, we have to list some of its terms. Let's see this. So to list the term of this sequence, let me write this in other form. If you divide this, both the numerator and denominator, by n, you get that result. This becomes 1 over n. This becomes minus 3n over n is minus 3. So minus 3 plus 1 over n on the numerator, and the denominator part, if you divide by n, 2 plus this 5 over n. This is it. So now let's just put some of its terms. So the first term we can put here. When you put 1 here, this becomes negative 2 over 7. When you put 2, this becomes 1 minus 6 is negative 5 over 9. It goes on like this. When n gets bigger and bigger, it proceeds, or it goes to which part? Let's assume here n is very big number. In this case, 1 over big number, this part is 0. Not only that, if you take this one, 5 over big number is also 0. The final answer for this will be this negative 3 over 2. So at infinity, this result, or this sequence, goes to negative 3 over 2. Negative 3 over 2. So when you see the value of this sequence, or the interval in this sequence found, let me put like this. When you see these numbers, it's getting increasing. By the way, negative 2 over 7 is here. Negative 2 over 7 is here. So from negative 2 over 7, the value is decreasing. So the value is decreasing. So you will find negative 3 over 2 here. Therefore, the value of this sequence found between negative 3 over 2 and negative 2 over 7. 2 over 7 is the part of our sequence, so it includes negative 2 over 7. Therefore, from this set, you can just list this upper bound. Upper bounds of this sequence are all numbers which are above this one, greater or equal to negative 2 over 7. And its lower bounds are all real numbers which are found below this one, including negative 3 over 2. So all numbers less than or equal to negative 3 over 2 are its lower bounds. And it is least upper bound. From the upper bound, the least one is the number, this number which is found at the border. So the least upper bound is this negative 2 over 7. And the greatest lower bound from the lower bound is the greatest one. You can see this. All these values are lower bound. From the lower bounds, the greatest one is this minus 3 over 2. This is it. Now let's see another part, monotonic sequences. Monotonic sequence. So a sequence AN is said to be monotonic or a monotone sequence if it is either increasing or decreasing. So a sequence, we call it this monotonic sequence if it is either increasing or decreasing. So let's see example for this. Check whether this one is a monotonic sequence or not. To check this, we need to just list the terms of this sequence. If you list the terms, the first term, when you put 1 in place of n, you get negative 1. The next term, negative 1, the power of 2, it is positive 1. The third term, negative 1, the power of 3 is negative 1. So it goes on like this. So when you see this, it is neither increasing nor decreasing sequence, because the higher term is not greater or equal to the preceding term, or it's not less than or equal to the preceding term. So I hope you remember to check whether a given sequence is increasing or decreasing. To check that, simply the an plus 1 term is greater or equal to the preceding term. In this case, we call the sequence is increasing. When you see this, the an is plus 1, if you take this one, it's negative 1, it's not greater than the term preceding it, so it's not increasing. To say decreasing, the an plus 1 term must be less than or equal to the term preceding it. So if you take this one and negative 1, when you compare these two, 1 is not less than this one. So this sequence is neither increasing nor decreasing. So because of this, is not a monotonic sequence, because it is neither increasing nor decreasing. Okay, now let's see a second example. Look, this one. 1 over n is given. So we are asked to determine whether this sequence is a monotonic sequence or not. To check that, let's list the terms of this sequence. When it just lists the terms of the sequence, the first term of this sequence, it is 1, and second term, when you put 2, it is 1 over 2. The third term is 1 over 3. It goes on like this. As you can see, this sequence is decreasing sequence. The terms are decreasing. Because of that, we call this is monotonic sequence. This is monotonic sequence. Okay, now let's continue the other part. That is about null sequence. Let's define what a null sequence means. A sequence an is said to be a null sequence if and only if the limit of an when n goes to infinity is 0. So we say this sequence is a null sequence if the limit of that sequence when n goes to infinity is this 0. Now let's see example for this. The first example, check whether this one is a null sequence or not. We are asked to check whether it is a null sequence or not. As you can see, the limit of this sequence when n goes to infinity is the denominator becomes bigger, or infinity. 3 divided by a bigger number at infinity will goes to 0. The limit of this sequence at infinity is 0. So this sequence, it is a null sequence. It is a null sequence. Now the second example, this example is given. It is n squared plus 1. We are asked to check whether it is a null sequence or not. When you just check or evaluate the limit of this sequence when n goes to infinity, infinity squared plus 1, a big number plus 1, it's a very big, it doesn't go to 0. Because of this sequence is not a null sequence. It is not null sequence. Now let's see about convergent and divergent sequence. Convergent and divergent sequence. Now let's see the definition. Let an be a sequence if the limit of an when n goes to infinity is a specific number L where this L is a unique real number. It must be unique where L is a unique real number. Then an is a convergent sequence and it is converges to L. If such a number L does not exist, we say that the sequence an diverges. We say the sequence diverges if L doesn't exist. So let's see example for this. When you see this sequence, the terms, if you put the terms of this sequence, it is the first term is this -1, the second term 1, the third -1. It goes on like this. So at infinity, this sequence goes to 1 or -1. When n is even number, big even number, the sequence goes to 1. When n is a big odd number, the sequence goes to -1. Since at infinity, this sequence does not goes to a unique number. It's not unique. It goes to 1 or -1. Because of this, the limit of this sequence does not converge. So it is a divergent sequence. Now, let's see this example, second example, sine 1 over n. Look this one. When n goes to infinity, at infinity, this number is infinity 1 over very big number, or 1 over infinity. When you take this ratio, this value goes to 0. So sine 0 goes to 0. So the limit of this sequence as n goes to infinity goes to 0. It goes to 0. Because of this unique number, because of this sequence is a convergent sequence. So this sine 1 over n is a convergent sequence. Now note this one. If a monotonic sequence is unbounded, if it's not bounded, it's unbounded, in that case the sequence diverges. If a monotonic sequence is not unbounded, it diverges. If it is bounded, then it converges. A bounded sequence, it always converges. Increasing bounded sequence, assume this one, A1, A2, it's getting bigger. Increasing bounded, it's a bounded sequence but increasing. In that case, the sequence converges to the least upper bound of that sequence. If it is decreasing, converges to the greatest lower bound of that sequence. So this is it. If it is a bounded sequence and increasing, in that case, it converges to its least upper bound. If it is a decreasing sequence and bounded, in that case, it converges to the greatest lower bound of the sequence. Now, let's see example for this. If you take this one to the power of n, if you try to list the terms of this sequence, the first one is 2, the second one 4, the third 8. It goes on like this. As you can see, this sequence it is a monotonic, or it's increasing sequence. But this sequence is not bounded, because at infinity this number is getting bigger and bigger and bigger. It has no upper bound. So because of that, this is not bounded sequence. Therefore, this is unbounded monotonic sequence. So it diverges. So unbounded sequence, we say it always diverges. Now let's see second example. 1 over n. If you take this one, if you list terms of this sequence, the first one is 1, 1 over 2, 1 over 3. It goes on like this. So it's decreasing. So it is a monotonic sequence. We said earlier, this one is a monotonic sequence. And this at infinity, it converges to, we can see this one in this form. The terms of this sequence are 1 over n. It's found between 0 and 1 including, and it's decreasing. So it's a bounded sequence. So at infinity, since it is decreasing, it converges to 0. It's the least upper bound of the sequence. So this one is a bounded monotonic sequence, and since it is decreasing, it converges to the greatest lower bound, which is 0. Okay. Now let's try to evaluate limits of a sequence. Let's start from this one. The limit of 2 minus n over 3n minus 5, where n goes to infinity. To evaluate this limit, first we need to divide both the numerator and denominator by n. So you will get this one. When you divide by n, this is 2 over n minus n over n is this 1 over, when you divide this by n, it is 3 minus this minus 5 over n. So at infinity, when n goes to infinity, this result goes to 0. 2 over infinity, it is 0. So 0 minus 1, it's minus 1, divided by the denominator part, 3 minus 5 over n. When n goes to infinity, this number goes to 0. So the limit of this sequence at n goes to infinity will be this negative 1 over 3. This is the answer. Now let's continue to the second example. Okay, the limit of to the power of n times 3 to the power of negative n, where n goes to infinity. To evaluate this limit, we can rewrite this in this form. It's the limit of 2 over 3. This number, 3 to the power of negative 1, can be written as 1 over 3 to the power of n. So the ratio will be this 2 over 3 to the power of n, where n goes to infinity. If you remember this, it's a geometric sequence, by the way. It's a geometric sequence with a common ratio 2 over 3. Or in other words, if a the power of n, where a found between 1 and negative 1, the limit of a the power of n when n goes to infinity always goes to 0. Using this concept, here this number is between 1 and negative 1. So the limit of this sequence goes to 0. It goes to 0. Now let's see the third example. To evaluate the limit of this sequence, we need to divide both the numerator and denominator by the square root of n squared. So when you divide by n square root of n squared, you get this one. Look, this is equal to the square root of n squared plus 1 over n squared. We are dividing by square root of n squared. The denominator part, square root of n squared, means this n, so this will be this n plus 1 over n. So this result will be this, the limit n goes to, this becomes n squared over n, is this 1 plus 1 over n squared, divided by this 1, n over n is 1, 1 plus 1 over n. So at infinity, this goes to, this part goes to 0, and this part also goes to 0. The final answer will be this, the square root of 1 over 1, it will be 1. This is it. So to summarize what we have seen today, these are the basic or the core points. The first one is n is said to be an upper bound of a sequence if this n is greater or equal to all terms of the given sequence. Second, m is said to be a lower bound if this m is less or equal to all terms of the sequence. And a sequence an is said to be monotonic sequence or a monotone sequence if it is either increasing or decreasing. The other point we have seen today is null sequence. A sequence an is said to be null sequence if the limit of that sequence when n goes to infinity is 0. And the other point, if this sequence is given, if the limit of that sequence when n goes to infinity is L, where L is a unique real number, in that case, that sequence is a convergent sequence. Otherwise, if this L doesn't exist, in that case, the sequence, we say that sequence diverges. So this is all about today's lesson. So for you to try, I'll give you exercise. Please try these questions by yourself. I'll give you to copy these questions. So this is all about today's lesson. I'll see you on the next lesson. Until then, goodbye.